Good day to Dr. Afis, and today I'll be presenting about my assignment, which is system modeling and analysis. And these are my group mates. Firstly, Farhan Nur Alia, Ina Erwina, myself Priya, and Atib Irfan and Azrin Najmi, and we are from group 7. As for the introduction, in this project, an electrical network with resistor, inductors, and capacitors, which is RLC elements, will be analyzed using control system concept and through MATLAB software. As for the part A, there will be a system modeled using frequency domain where the transfer function of the system will be developed, and we will use that transfer function to evaluate unit step response, determination of transition response specifications like rise time, settling time, percentage overshoot, as well as finding the poles and zeros of the system. As for the next part, we will use that obtained function from part A to part B to form a state space equation, a state space model, a unit step response of system, and finally there will be comparison of results obtained from the use of both transfer function and state space methods. And throughout this project, we gained practical experience in system modeling, stability analysis, and simulation using MATLAB. Okay, now I'll be moving on to part A, which is frequency domain modeling and analysis. And now I'll be explaining about the calculation of the transfer function. So as for the first step, I labeled the parameters in the circuit and did the loops. So as we can see, L1 and L2 is equals to L1 equals to L2, so it's 2.2 microhenries, and C1 is equals to C2, which is 7.5 microfarads, and R1 equals to 30 ohms, R2 equals to 22 ohms, and R3 equals to 10 ohms. And this is the first loop, second loop, and third loop. So as for the next step, I converted this into S domain. So the L will be SL1, the L will be SL1, and L2 will be SL2, and C1 will be 1 over SC1, and C2 will be 1 over SC2. And I labeled the nodes VB, VA, VC, and VD. So let's get into the calculation. So as for the KCL for node B, so what I did was I followed this direction. So it's going to be VB minus VA over SL2, as we can see here. And for the next direction, I followed this way. So it's VB minus VA over L1 plus R1, as we can see here. And the next direction is the upward, so it's VB minus VC multiplied by C1, which is here, and equals to 0. And I substituted all the values, and before that I brought this VA to the left side and substituted the values. And nextly for KCL for node C, which is this, firstly I followed this direction, so it's VC minus VA over R2, and then this direction, so it's VC minus VB multiple C1, and lastly this way, so it's VC minus VD over C2, A multiplied by C2 multiplied by C2 equals to 0, and I brought the VD to the right side and substituted all the values in. Lastly, for KCL for node D, which is there, so it's just one component here, so it's VD over R3, and then VD minus VC multiplied by C2 equals to 0. Substituted all the values. And for the next step, I did the simultaneous equation in matrix form. So basically, I just basically I just substituted all the values here for BB. From node B, I took this answer and put it here, and VC and VD. And the vectors is VA, took it from node B, this one, VD, and the node D. And for the next step, to find the determinant of the coefficient, it's determinant equals to modulus of A. So just took the matrix form and did the modulus, and to expand, and the next step we expanded. So this first equation goes outside and cross multiply this one and minus by this row, so cross multiplied here and did all those expense and ended up with this equation. And okay, and next part, to find the determinant of for VC, basically took the matrix form and just substituted the second row with the vectors and did the same process all over again, and then we expanded and we got with this answer. And finally, to find the determinant of VC, to find the VC, we took the answer we got from the previous determinant C over determinant from the very first answer and divided. And for VDs, just do not be times into VC, and VC2 will be VC minus V2. And this is the substitution of it. And the last answer is this: 1 over 30 divided by 1 over 10 plus 1 over 7.5 times 10 to the power of negative 6 multiplied by VC. So since now we have VC2 and VIS, we can just substitute the values in. So for the VC, this is the VC equation divided by the VI. This is the VC2 equation and divided by the VI, which is this one. And as we brought the VI to this up, it's going to be multiple, and this is the multiple answer. And as for the final answer, it's going to be 3.30 times 10 power to 14 S3 plus 7.80 times 10 to the power 21 S square plus 7.80 times 10 to the power 21 S square, 4.5 plus 4.50 times 10 to the power 23 S plus 2.72 times 10 to the power 32 over 7.92 times 10 to the power 10, and S4 plus 1.5753 times 10 to the power 18 S3 plus 3.39 times 10 to the power 24 S square plus 5.83 times 10 to the power 24 S plus 2.72 times 10 to the power 32. So this is our final transfer function. Thank you.
Assalamualaikum, my name is Ina Erwina binti Abdul Mahid. Number matrix P122410655. Next, I will explain about the unit step response analysis of the transfer function. After obtaining the transfer function, we use the MATLAB step function to simulate the system response when a unit step input is applied. We also use the step info command to calculate the transient response parameters automatically. From the simulation result, the rise time is approximately 0.8 millisecond, which means the system reached its desired output very quickly. For the settling time is about 1.26 millisecond, showing that the response becomes stable in a very short time. And the percentage overshoot is 0%, which means the output does not exceed its final value. This indicates that the system is well done with no oscillation occurring during the response. And then the steady state value is approximately 0.9994, which is very close to the input value of 1. This shows that the system has a steady gate gain close to unity and can accurately follow the input signal. For overall, the unit step response demonstrates that the system is fast, stable, and highly damped, making it suitable for reliable operation. Next, I will explain about pole zero analysis. We determine the location of the poles and zero of the transfer function and display them using the pole zero maps, which is this graph. MATLAB also check the system stability by examining the real paths of all poles. Based on the result, all poles are located in the left half of the S-plane. Since every pole L has a negative real value, the system is stable. And then the negative pole location indicate that the transient response naturally decays over time without producing sustained oscillation. This explains why the unit step response has 0% overshoot and reach the steady state value quickly. So for the pole zero analysis and the unit step response consistently confirm that the electrical system is stable, well damped, and capable of producing a smooth and reliable response.
I will be present part B, state space modeling analysis. For first, state space derivation. We begin the state space derivation by using the transfer function Gs equal to Vc2 over Vi. The numerator and denominator coefficient are first normalized by dividing them by the leading denominator coefficient, which is 7.92 times 10 power of 10. To obtain a standard transfer function with a unity leading coefficient. From this normalization process, the coefficient A0 to A3 and B0 to B3 are calculated and substituted into the transfer function. Next, the transfer function is separated into the state equation and output equation form. By applying the inverse Laplace transform, the denominator polynomial is converted into a fourth-order differential equation. This allows us to define the state variable and prepare the system for state space representation. The resulting normalized transfer function and calculated coefficient from the foundation for deriving the state equation, output equation, and the state space matrix that will be present on the next page. This is the next page. On this page, the normalized transfer function is converted into its state space representation. First, the inverse Laplace transform is applied to obtain the fourth-order differential equation of the system. For state variable are then defined as x1, is x, x2 is x dot, x3 is x double dot, and x4 is x with triple dot. Allowing the higher order differential equation to be expressed as for first order state equation. From this equation, the state matrix A and matrix B are construct where matrix A represent the system dynamic and matrix B represent the effect of the input voltage, which is Vi in bracket T. Next, the output equation is derived from the numerator of the transfer function and expressed in terms of the state variable, resulting in the output matrix C. Since there is no direct relationship between the input and output, the feed-through matrix D is equal to 0. Therefore, the matrix A, B, C, and D fully described, and the system in standard state space form, which can be used for system analysis simulation and controller design. We can start in section 1 by plugging in our specific circuit value with 3 resistor, 2 capacitor. Moving to section 2, instead of dealing with a massive equation for our transfer function, we just put those huge coefficient numbers into two simple array and use the tf command to let MATLAB build the function g for us. Finally, in section 3, conversion state space representation. We wanted to look at the system internal dynamic. So we use the ssdata command to convert everything into an optimized balanced state space model. The script wrapped up by cleanly printing out our A, B, C, and D matrix. So they are ready for simulation. For this page, we have realization B, programmatic generation of control canonical form. Instead of using MATLAB built-in canon command, which actually crashed here due to a numerical singularity, we bypass the glitch by extracting the transfer function polynomial with TF data and build the companion matrix directly by normalizing them with the leading denominator coefficient. This gives us the exact theoretical hand calculation layout for our A, B, C, and D canonical matrix. Finally, in section 4, we jump into the time domain and transient response analysis. We use the step info command to instantly grab our key performance metric like rise time, settling time, percentage overshoot, peak time, and peak value, and wrap things up by using DC gain to find our steady state gain K. All of these parameters are cleanly printed out at the end. So this is the result and plot, which you can see in this image. Up top MATLAB printed out our continuous time transfer function G is a third order numerator over a fourth order denominator with some massive coefficient in scientific notation, which perfectly capture our circuit frequency domain behavior. Right below that, you can see the result of our internal balance. State space conversion matrix A is a 4 times 4 matrix scale by a factor of 1.0 times by 10's power of 7. Matrix B is a column conversion, is a column vector starting with a value of 512. Matrix C gives us our 4-row vector output, and matrix D is simply 0, confirming there's no direct feed-through from the input to the output. These clean, balanced numerical values are exactly what we need to ensure our subsequent simulation runs stably without any rounding or scaling error. Next, we have the output for our theoretical controller canonical matrix and our transition response parameter. For the matrix up top, you can see the classic component or hand calculation layout. Matrix A Matrix A has its standard identity shift row by row with the normalized polynomial coefficient sitting along the bottom row, scaled heavily by 1.0 times 10 power of 21. Matrix B is our clean canonical input vector ending in a 1. Matrix C hold our numerator coefficient and matrix D is 0. Next, transition response parameter. MATLAB calculate our exact time domain performance matrix. Our system respond incredibly fast with a rise time of just under 0.66 millisecond and a settling time of about 1.27 millisecond. We have a percentage overshoot of 0%, meaning the response smoothly climb without any oscillation or ringing. It reached a peak value of practically 1 volt, which is 0.9929 volt at around 3.37 millisecond, matching our calculated steady state gain, which is K of exactly 1.00. This tells us our circuits acts perfectly as a stable unity gain system with no signal attenuation over time. Here our output voltage VC2 plotted over a window of 4 milliseconds. As you can see, the solid blue line representing our S-domain transfer function model and the dashed red line representing our state space realization. They trace a perfectly smooth, critically damped curve that quickly climb at and stabilize right at a steady state value of 1 volt because the two curves overlap completely without a single millimeter of deviation. It visually proves that our mathematical conversion and coding logic are 100% correct, showing identical system dynamic across both methods. That concludes our look at the visual result, and now I will turn the presentation over to pass to my friend.
Bismillahirrahmanirrahim. My name is Muhammad Rifan bin Muhammad Zaili. My matrix number is B1224100130. So, moving on to our discussion of observation, we analyze the system from two angles. First, we look at it from the outside using the transfer function format, looking specifically at how it responds to a sudden input, a unit step response. What we found is that our system is incredibly stable, fast, and smooth. Here are the three main things we observe. First, it tracks perfectly. Our steady state output reached 0.9994, which is practically a one-to-one match with our input of 1. This means the system has a gain close to unity. What you put in is what you get out. Second, there is absolutely zero bouncing. We recorded exactly 0% overshoot because the system is heavily damped. The signal doesn't overshoot or ring. It just climbs smoothly straight to the target. Third, it is remarkably fast. It takes just 0.8 milliseconds to rise up and completely settles into its final target zone in just 1.26 milliseconds. When we look at our pole zero analysis, the math perfectly back this up. All of our system poles are located in the left half of the S-plane. In control theory, left half poles guarantee that any initial spikes or transition energy will decay safely over time, resulting in a smooth, stable response without any oscillation. Moving on to part B, the state space representation. While the transfer function look at the system from the outside, state space look inside the RLC network. We use the controller canonical form to organize our equation um, from Ocean. The main benefit here is total transparency. The rows and matrix are perfectly mapped out the exact same characteristic as our transfer function. It proves that no data was lost when we change formats. To check internal stability, we extract the agent values from our system matrix A. As you can see, uh, we obtain four distinct negative real agent values. Because these agent values are strictly negative, it satisfies the requirement for absolute stability. Physically, this means that any transition energy temporarily stored inside our circuit's reactive component, our inductor and capacitor, will naturally and safely drain out through our resistor over time. The system will always stay bounded and under control. To conclude our observation, we tie this time domain matrix directly back to the physical component of our group circuit. Why did we get 0% overshoot? Because our internal circuit resistance are large enough to act as a heavy cushion, completely killing off any inductive capacity ringing. Second, why is it so fast? Operating in microsecond. Because our energy storing components are tiny. Microscale values like a 2.2 micro H inductor and a 7.5 micro F capacitor charge and discharge almost instantly. Number three, why is the final tracking so accurate? Under steady DC condition over time, inductors naturally behave like short circuit closed wires, and capacitor behave like open circuit broken wires. This structural transition forces the final output voltage to perfectly match the input voltage. Overall, both our external transfer function and internal state space observation confirm the exact same thing. Our RLC network is fast, highly stable, and completely free of unwanted oscillation. Thank you.
Assalamualaikum and good morning. My name is Farhanur Alia binti Fasasli Kamal. My metric number is B122410116. Um, for my part is comparison for simulation and theoretical result. Let's look closely at the performance metric obtained for our group. We got G7 RLC electrical network under standard unit step input as summarized on this slide. The alignment between our hand-derived theoretical expectation and the automated MATLAB simulation parameter is nearly perfect. The minor discrepancy in the final steady state amplitude 1 versus 0.994 is purely tracking artifact of numerical approximation tolerance during MATLAB. Uh, this negligible variation confirms that our derived transfer function perfectly models the real-world reactive network behavior. From this comparative result, we can draw three critical physical insight regarding our circuit characteristic. First, the 0% overshoot indicates the circuit is heavily overdamped. The initial loop resistance R1 equal to 30 ohm, R2 is 22 ohm, R3 is 10 ohm. Supply sufficient damping to entire suppress any inductive capacitive, resonant, ringing, or transient tracking oscillations. Second, the microsecond response window featuring a rapid rise time of 0.8 millisecond is driven entirely our microscale energy storage element, which is L equal to 2.2 micro and C equal to 7.5 microfarad. Third, the steady state tracking accuracy highlight that as the approach infinity under constant DC excitation, the inductor capacitors into short circuit and the capacitor into open circuit. This structural transition allows the output voltage across C2 to track the input voltage seamlessly. When moving from the frequency domain to the time domain, in the part B, evaluating the system matrix A lets us extract the internal equivalent directly. As display, our state space equivalent match our transfer function poles exactly, falling at S1 equal to 1.7436 times 10's power of 7, S2 equal to minus negative 2.4210 times 10's the power of 6, S3 equal to negative 3.000 times 10 the power of 4, and S4 equal to negative 3 times 10 the power of 3. Because all four equivalents are located strictly in the left half of the S-planes, the system meets the criteria for asymptotic stability. Any transient energy stored within our reactive component safely dissipates through our resistive element over time, producing an identical bounded step response curve. In conclusion, our all primary objectives of this project have been successfully fulfilled. We have effectively demonstrated that classical frequency domain modeling and modern state space realizations provide mathematically equivalent windows into internal system states. The excellent agreement between our calculation and the MATLAB verification confirm the absolute validity of our mathematically models, providing us with invaluable hands-on mastery over control principle and transient analysis technique used in advanced electrical engineering. Thank you.